In the middle of 4.3, we're talking about solving second-order, linear, differential equations with constant coefficients. Fairly specific, but we're going to be able to generalize to more cases in a moment. In this case, we're looking at this guy. In fact, add one more modifier to that. We're looking at the homogeneous case where the right-hand side is 0. So something that looks like ay double prime plus by prime plus cy equals 0. And what we learned last time is that the way you solve that is to immediately write down your characteristic polynomial. So instead of having ay double prime plus by prime plus cy, you write down am squared plus bm plus c. Solve that, and then your general solution can be determined by the roots of that equation. Now, if there are two distinct real roots, it's as simple as this. It's y equals c1 e to the m1t plus c2 e to the m2t. The reason is up here. On the other hand, if you get a repeated real root, then it is c1 e to the m1t plus c2 t e to the m1t. And the extra t is in there because the roots are the same, so if you just wrote e to the m1t and e to the m1t, those were not linearly independent solutions. Okay? Now we're talking about the complex conjugate case. And while we have actually written down a solution that is somewhat satisfactory, it has some flaws in it. In particular, if I get a complex answer to the characteristic polynomial, I get complex roots, and I plug them in for my m, then I have c1 e to the a plus bi times t plus c2 a minus bi times t. And that is, in fact, a general solution. But what we don't like about it is that we started with a real equation, real in the sense that it only had real coefficients, and now our solution has complex parts to it. And we don't want that to happen, especially if our equation is modeling something in the real world over time, like a spring being pulled out of its equilibrium position and let go and allowed to oscillate. We would expect that the location of that mass at any given time, t, exists in real space. It doesn't have a complex component to it. All right, so what we want to do is we want to take Euler's formula and we want to rewrite the complex case, case 3, without any i's. So obviously the answer to that question is yes. That's why we're doing it. Consider this. Again, we have this piece up here, this e to the bi t. Let's say I have e to the b I t, I being that complex number. I'm going to factor out the e bt and just write that I off to the side there. And then apply Euler's formula right there. So now my theta is what's inside the parentheses. So this is cosine of bt plus I sine of bt. All right. Now, if I did the same thing with the negative part of that over on the previous page, b I t, applying Euler's formula gives me cosine of negative bt plus I sine of negative bt. And then I will use the fact that cosine is an even function, and sine is an odd function. Do you remember what that means to be even and odd? If it's even, what happens to this minus sign right here? Remember, cosine looks like this. So if I go to an x and get the height, if I go to negative x, I get the exact same height. Even means f of negative x is equal to f of x. Okay, that's an even function. Okay, cosine of negative x is the same thing always as just cosine of x. So I can drop the minus sign. This becomes cosine of bt. On the other hand, sine is an odd function. So that if I go up this way and down this way, it's the opposite. It's a reflection of it. F of negative x is negative f of x, or in our case, sine of minus x is minus sine of x. That's what it means to be an odd function. So I can do what with this minus sign? Well, I can pull it out front. I'm going to rewrite this down here slightly. This becomes cosine of bt minus I sine of bt. Okay, now I'm putting some Legos together to build a kind of final picture of what's going to happen here. Take 1/2 e to the bit minus 1/2 e to the negative bit. And tell me what you get. Actually, no, let's do plus. Just do plus first. So I'm looking at this and this. Now, if I were to just add those together, what happens? The sine bt cancels out, right? And I get 2 of these. So if I take half of this equation plus half of this equation, that's all I'm asking you to do right here. Do you see that that's the same thing as just cosine of bt? Again, take half of this, add it to half of this. And you get cosine of bt. And 1/2 e to the bit minus 1/2 e to the negative bit. If I subtract them, what do I get? So this equation minus this equation, and then with a 1/2 out in front of it. I sine bt. Okay. So now here's the final construction of this. Recall that we said y equals C1 e to the at times e to the bit. That was, I'm going to just scroll up so you can see it. This part right here. Actually, let me just write it in this form that's right here at the bottom of the page. So actually, let's pull the e to the at out and write it as C1 e to the bit plus C2 e to the negative bit. was a solution for all C1 and C2. Right? So, if C1 and C2 are both 1/2, notice that means y is equal to e to the at 1/2 e to the bit plus 1/2 e to the negative bit. What is that equal to? Yep, with the e to the at out front, right? E to the at cosine of bt. So here is a solution without any i's in it. Just draw an arrow. That's now a solution. E to the at cosine of bt is a solution to the original differential equation. Okay? Now, if C1 equals 1/2 and C2 equals negative 1/2, we get y is equal to e to the at 1/2 e to the bit minus 1/2 e to the negative bit, which gives me e to the at I sine of bt So if this is a solution, then so is e to the at sine of bt is also a solution. Now, why is that true? That's true because of the superposition principle. If you have a solution, you can multiply it by any constant, and it's still a solution to the homogeneous equation. And that's all I'm doing. So really what I've got now is I've got two new solutions, this guy and this guy. If your root to the characteristic polynomial is a plus or minus bi, then e to the at cosine of bt is a solution, and so is e to the at sine of bt, with no i's in them whatsoever. So your general solution will now look like this. And put a big star by this. Your general solution, instead of writing it with e and I exponents, you can write it as y equals c1 e to the at cosine of bt plus c2 e to the at sine of bt. So all of that explanation to get to this. Now we know that whenever we solve the characteristic polynomial, if we get two real distinct roots, we use the first case. If we get the repeated root, we use the second case. If we get a complex root, then we use this final solution right here. It all depends on what the roots to the differential equation look like. Okay? At that point, you should see that this is a very easy thing to now do. I mean, if I give you any homogeneous, linear, second-degree differential equation, it's as easy as solving a quadratic equation. And you're done.
How did we get the solution y equals e to the at sine bt without the I?
Well, I use the superposition principle. What I'm basically doing is saying that if any solution can be found to the homogeneous equation, you can multiply it by any constant real or complex, and it's still a solution. So I'm basically just, if this is a solution, then negative I times that is also a solution. Okay, I can just drop constants. Okay, if y is a solution, then cy is a solution. And in that case, I'm just choosing the c to be negative I. Because if I multiply this by negative I get negative I squared, which is positive 1. So that's also a solution. And now I've got two solutions, and so any combination of those two is also a solution. So that's how I get the general solution down here without any i's in it. All right, so let's do these. I can do these in probably a couple minutes flat. So first of all, if I give you an equation that looks like this, you identify that it is linear, second order, constant coefficients, and homogeneous. In those cases, how do we solve it? Step 1, write down the characteristic polynomial. What is the characteristic polynomial? 2m squared minus 5m minus 3 equals 0. See where that came from? Now do your algebra. Solve that. You can use quadratic formula. Probably in this case, factoring is easier. I think it's
2m minus 1 and m equals negative 1.
2m minus 1 and m plus 3?
Yeah.
So negative 1/2 and 3. Or positive 1/2 and negative 3. Now I think it should be 2m plus 1 and m minus 3, right? Yep. So this is negative and this is positive. 2m plus 1 times m minus 3 gives me those two. You get two distinct real roots. What's your general solution?
Y equals c1 e to mt plus c2 e to m2e.
So our m1 is
Negative 1.
plus c2 e to the 3t. So what happens to this guy in the long term? What happens to this term as t goes to infinity? 0. What happens to this one as t goes to infinity? It blows up. So this whole thing blows up, goes to infinity. 0 plus infinity is always infinity. All right. Solve this one. What's your characteristic polynomial?
M squared minus 10m plus 25.
M squared minus 10m plus 25 equals 0.
M minus 5, M minus 5.
It's a repeated root. So what's your general solution?
C1 e to the mt plus C2 t e to the mt.
So C1 e to the
5t.
5t plus C2.
T e to the 5t.
So for repeated roots, you put a polynomial out front, actually just a t factor. If it had been repeated 3 times, we're only doing order 2, so we couldn't have 3 roots, but we will see in a moment we can have higher orders and it's still solved the same way. Well, in that moment, we'll talk about you can just keep using higher and higher powers of t there. Nikolai, you had a question?
Yeah. So why are we writing the general solution like this if in the previous section we just said there's supposed to be a cosine and a sine? No, down below.
Because example 1 was case 1. 2 distinct real roots. So I used this one.
Oh, okay.
The example 2 was a repeated root, so I used this one.
Okay.
In a moment, we'll get one that has complex answers. Remember, complex is whenever in the quadratic formula, if you get a negative underneath the radical, then you'll have i's. Then you'll use sines and cosines.
Okay. Then that's when we'll use the one we just
Yep.
created. Okay.
So let's try that. I think that's probably what this one is. M squared plus 4m plus 7 equals 0. This one does not factor, so use the quadratic formula. X is equal to negative b plus or minus the square root of b squared minus 4ac over 2a. Gives me a negative 4 plus or minus a negative 12, square root of negative 12 over 2. Square root of negative 12 is 2I root 3. All right, you can pull the 4 out, side becomes 2. Take the negative out, becomes I. And then the 2 divides into both terms in numerator, so I get negative 2 plus or minus I square roots of 3. Okay? So, in this case, now, what's my A and what's my B? What's my real part, what's my imaginary part? A is negative 2, B is root 3. So what's your general solution look like now if we apply the one we just came up with in case 3?
We want to use the one we just created.
Yeah.
We don't go back to that.
Don't use one that has complex numbers in it. Don't use what's at the bottom of page 2. We've come up with a better form to write our answer in so that we can write it without needing complex numbers to express the general solution. C1, e to the at, negative 2t, times cosine of bt, square root of 3 times t, plus C2, e to the negative 2t, sine, square root of 3t. Or what is sometimes more commonly written, and the only reason I'm going to write it like this is to talk again about the long-term behavior, and it's easier to see it. Well, it's actually not that much easier to see it. But I can pull the e to the minus 2t out and have it only written once, and then have C1 cosine of root 3t plus C2 sine of root 3t. But this now solves that differential equation. In fact, that's what we've done in every case. All of our y's, the last 3 examples, solve the original differential equation. And just, again, if you've forgotten where the line of reasoning came from, it all started with us making a guess up here of what the solution might look like. We try to form e to the mt, and then we plugged that into here, and it reduced down to this characteristic polynomial. And when we solved that, we came up with two possible values for m, making each of them a solution. And then your general solution is the linear combination, C1 of one plus C2 of the other. There we go. All right, let's do one initial value problem just for completeness sake. So in addition to solving the differential equation, we're now going to find the c's. All right, so it's second order, it's linear, it's got constant coefficients, there's no x's in front of the y's, and it's homogeneous. That means we can solve it directly by the characteristic polynomial. So what is the characteristic polynomial in this case?
4m squared plus 4 rounded to 17. 0.
So m is negative 4 plus or minus the square root 16 minus 4 times 4 times 17 divided by 8. What's 4 times 4 times 17? Is that 272? Is that right? So 16 minus 272 is a minus 256? And that's 16 squared. So negative 4 plus or minus 16i over 8. Yeah, so that's like negative 1/2 plus or minus 2i. Good night. So what does our general solution then look like?
Well, you got C1 t to the negative 1/2 t. That's times cosine to R2t.
Mm-hmm.
And then plus C2 e to the negative 1/2 t sine 2t.
Okay. So now let's use our initial conditions to find the c's. If I plug in 0, I get C1, e to the 0 is 1, cosine of 0, which is, by the way, 1. Should I write all this out? I think I'm going to write it all out. E to the negative 1/2 times 0 cosine of 2 times 0 plus C2 e to the negative 1/2 times 0 sine of 2 times 0. So this here is 1, this is 1, this is 1, but this is 0. And all of that has to be equal to negative 1. So I get C1 equals negative 1. This is where it gets a little messy. We got to now find y prime. Are y'all with me on C1? Okay. So now y prime, I've got two terms. Both terms are product rules. So first times the derivative of the second, and the second's going to have a chain rule in it too. So C1 e to the negative 1/2. Actually, you know what I'm going to do? I'm going to make my life a little bit easier. I'm going to do this as one product rule instead of two. E to the negative 1/2 t times C1 cosine of, I'm not taking the derivative yet, by the way. Cosine of 2t plus C2 sine of 2t. Okay, so that means y prime would be, let's do the derivative of the first times the second. So negative 1/2 e to the negative 1/2 t times C1 cosine 2t plus C2 sine 2t plus the first times the derivative of the second, which is e to the negative 1/2 t, and the derivative of C1 cosine of 2t is going to be negative 2 C1 sine of 2t. Because the derivative of cosine is negative sine times the derivative of what's inside, which is 2. Plus 2C2 cosine of 2t. I mean, essentially, if you did the product rule on each one of these separately, you still get these essentially 4 terms there. So that works. That works. Are we okay? Good so far? We're just taking derivatives, so you want to make sure and double check that you can take the derivative on that. Do you see any mistakes that I've made, or does that look right to you? I'm not seeing any wrinkled forehead, so I'm plowing forward. Y prime of 0 then. And I'm gonna go ahead and plug these in my head. I know that the e to the zeros both become 1s. I know that the cosine of zeros become 1s. And all the sine of zeros drop out because they're 0. So I think I get negative 1/2 C1 plus 2C2. And that has to equal 2. We're going to set that equal to 2 from up here. Now if I plug in C1 is negative 1, I get negative 1/2 times negative 1 plus 2C2 equals 2. That's a positive 1/2. Subtract the other side, I get 3/2. It's equal to 2C2. So C2 should be 3/4. So that means my y is equal to, plugging in C1 and C2 into my general solution, negative e to the minus 1/2 t cosine 2t plus 3/4 e to the negative 1/2 t sine of 2t. So what happens to that? Oh, well, before I ask that question, is that okay with everybody? You got the process fairly well down? Before we jump to the next page, let's explore this. Let's kind of unpack this a little bit here. First of all, what happens to this as t goes to infinity?
Both terms approaching 0.
So the whole thing goes to 0, right? Because this, as t goes to infinity, you get e to a very large negative number, which goes to 0. The cosine of 2t just keeps bouncing back and forth between negative 1 and positive 1. So does sine. But as you're multiplying by something getting close to 0, then that forces this term to go to 0 and this term to go to 0. So they both go to 0. In fact, that kind of gives you an idea of what this picture of this graph might look like. If you have an e function, that's pushing this thing to get smaller and smaller as you go out. And the cosine and the sine are making this wave bounce back and forth, right? So the wave should start out big and then start to get small over time.
Big as 1.
Yeah. Big as in compared to where it is way down there at the end. But yes, starts out at right 1, right, and then shrinks. Which, if you're thinking about a spring with some damping on it, like a friction, like it's sliding against the surface on which it's riding, that's what you would expect to happen. So imagine I got a wall here, a spring here, and a mass on it, and it's sitting on a table, right? And I pull it this way, what's going to happen to that mass? It's going to pull back this way, but it's going to go past the equilibrium, and now the spring's going to start pushing and going back this way, but the friction is slowing things down, which is exactly the kind of wave we're talking about, right? If we look at a graph of this, in fact, I'm going to jump out of this even now, and I'm going to go into Wolfram Alpha, because it loads faster than Maple, and that's the only reason I'm doing it. I'm going to plug in our function that we just got, which was negative e raised to the negative 1/2 times t plus, or times cosine of 2t plus 3/4 times e raised to the negative 1/2 times t times sine 2t. That looks right. Okay. So starting at 0 and moving from there, notice that's the behavior you get. We really don't care what's happening over to the left-hand side. In the application of thinking of it as a spring, we're going to start at time 0 and see what happens, how this thing evolves. And so it approaches 0, as expected. Okay? All right. I may have to go back and talk about springs and derive the equation for you here in just a minute. Last thing I want to do is just mention that the same technique that we just learned how to apply to second-order equations works for higher-order equations. So that's what last page of your notes on 4.3 are talking about. Higher-order differential equations. We're still talking nth order, we're still talking homogeneous, and we're still talking constant coefficients. Actually, we're now talking about nth order. So the only difference is instead of being the highest derivative is a second derivative, we can go up to a third derivative, fourth derivative, and so on. The characteristic polynomial is going to work exactly the same way, that you write it down to whatever power is the order of the derivative. So if I had a y triple prime plus 3y squared minus 4y, I can write the characteristic polynomial for this thing down here. Right? What would be the characteristic polynomial?
Y cubed plus 3y squared.
M cubed plus
Oh, sorry.
3m squared.
Minus 4m.
Oh, careful. That's the easiest mistake to make and probably the most common. Y is the 0th derivative. So you don't have an m. M represents a first derivative. So you just have a constant term. Remember up here on these, like this one here, the 25y corresponded to no m into there. So remember that when you see a y, that's the constant term. So this becomes m cubed plus 3m squared minus 4. Equals 0. Before we write down the solutions to that, let's just recall. What we're going to do is when you have distinct roots, for every root that is a single root, you just have the component of your solution, your fundamental set of solutions that corresponds with that root is just e to the m1x. If you have repeated roots, then you include a term in your general solution for every time that root is repeated. So if it was only a double root, you would have an e to the mi, I don't know why I'm using x's now, but we'll use x's, and then x e to the mix. And mi doesn't mean I as in complex, but I as in, that's the ith root. That like m1, m2, m3, so on. E to the m1x, x e to the m1x. If it's repeated 3 times, you would have an x squared e to the m1x. If it's repeated k times, you go all the way up to x to the k minus 1. And whenever you have complex conjugates, for every complex conjugate, you have a term that looks like this and a term that looks like this. This, by the way, takes for granted the fact that you can factor or solve higher order polynomials than just quadratics, which is not always the easiest thing in the world to do. You don't have a cubic formula memorized. I'm almost certain of it, even though there does exist a cubic formula. You don't have the quartic formula memorized because it takes up a whole page to just write down. So I know you haven't got it memorized. And I know you don't have a quintic formula memorized because it doesn't exist.
We get a free homework pass for coming in.
Did you know,
Deciding.
like, back in the, I think it was probably the, when was this? I'm guessing like the 1700s. 1600s, 1700s. It was a thing for the academic elite to hold competitions, like public exhibition competition, not a boxing match or a race, but it was a math event where they would compete against each other solving polynomial equations. They would like have these big competition, but where one renowned mathematician versus another renowned mathematician, and the whole purpose of it was to see who could solve a given cubic equation. Not quadratic, because those were easy, everybody knew how to do those. But people would come to watch these people walk through how to solve a cubic equation. And then one person would challenge the other person with another cubic equation to see if they could solve it. I forget the guy's name. Maybe Tartaglia was like the champion of this. But he kept it to himself. He wouldn't publish what his secret cubic formula was. But nobody knew how to solve cubic equations in general. So if you could give him just a general cubic and he could solve it, it would be like, whoa, wow, and the crowd would go wild.
Sounds great.
Oh, man, good stuff. I mean, this one's hard enough. I mean, think about your life without Wolfram Alpha or Maple. If I ask you to find the m's that satisfy that equation, what are the 3 roots of m cubed plus 3m squared minus 4 equals 0? How would you do that? What are you trying?
I was just guessing.
So guess numbers. In fact, if you can guess one root, you can use long division to turn this into a quadratic. Right? Because all you got to do is, if say for example I told you that 1 was a root to that. I plug in 1 cubed plus 3 times 1 squared, that's 4, minus 4 is 0. So you can tell right away that this has to factor into m minus 1 times something. If 1's a root, that has to be true. So you could, at that point, do like m cubed plus 3m squared plus 0m plus 4, or minus 4, and divide by m minus 1, and you'll get no remainder. So the thing up here is not quadratic. You could then factor that or use the quadratic formula. So if you can get one of them, then you're done, because the rest is trivial. Turns out that's actually, I think you get m squared plus 4m plus 4 when you do that. Yeah. Which, by the way, how does that factor?
Cruise.
So m plus 2 squared.
Man, I gotta have something guessing.
So you've got a 1, a 2, and a 2. Now you can imagine how painful this would be if I didn't give you nice whole number roots or even integer roots, or if they're complex conjugates, yada yada. We've got algorithms in numerical analysis to try to handle a lot of these, but I guess what's kind of interesting about these characteristic polynomials is that when you get beyond cortex, degree 5 and higher, there is no guaranteed formula to find all the roots. We can only approximate in general. On the other hand, with cortex, there's a formula. It's huge. You should Google the quartic formula sometime. The cubic formula is not that bad. It's a couple, 3 lines long. It's not horrible, but it's certainly longer than the quadratic formula. But it has been proven mathematically that there does not exist a quintic formula or higher. There's no closed form formula to find all the roots of a degree 5 polynomial in general. It's not that we haven't found it yet. We can mathematically prove, using some group theory from abstract algebra, that no such formula even exists.
So can we get some bonus points for free homework for memorizing and reciting like
The cubic and the
cubic?
quartic, I might give you something for the quartic formula. That would be impressive.
It's just memorization.
A page-long memorization of a formula. You can't even remember what the power series for cosine was.
People do like what 10,000?
Yeah, 1,000 digits of pi or something like that. Yeah.
I think the record.
What's the general solution to this?
1,000? 10,000.
Sure, 10,000.
World record.
There's
That's really crazy.
solution. It's going to have 3 terms, a C1, a C2, a C3, because you've got 3 roots. One of them is repeated. The one that's not repeated is the easy one, C1 e to the 1t. Right? I'm using this form up here.
Is it negative 1? T?
Positive
Oh, never mind. Yeah, that's.
t. I'm sorry, I switched back to x's on this notes up here, but those meant to be t's. Plus
E to the negative 2k.
e to negative 2t plus c3
C3 T squared?
I don't know why I put negative in there.
It is a negative.
It is.
Oh, because of here. I didn't put my negatives over here. That's what it was.
Is there is it a T squared because it's a three value, or is it
No, you only include the number of terms. So you start with t to the 0, t to the first. Notice how it goes up to
the number of repeated terms?
minus 1 is the
So
last
it'd be
power.
Well, I guess it doesn't matter, but it would be actually C4 since the C3 term doesn't exist, I guess. Because it's 0, you know? 'Cause it's,
It doesn't matter. That would just
Yeah.
be the same.
I know.
It's the same
Well,
order.
Oh, you mean because there's a 0m up
because
here?
there's no. Yeah.
No, you always do it in terms of the number of roots to the equation, not how many terms there are up here. Right, so I'm getting an m equals 1, an m equals negative 2, and an m equals negative 2. So there's a C1 that goes along with the first root, right? This is like M1,
Yeah.
M2, and M3, right? That's what these little MIs up here are talking about. So for M1, there's just an e to the M1t. For M2 and M3, they are the same, so actually I'm going to call them both M2. M2, I've got e to the minus m2t, and then a t e to the m2t. Okay, so there's not a term that corresponds with each of the terms in the characteristic polynomial. There's only a term that corresponds with the roots of that. So let's assume that I had a particular differential equation, and I went through the process of identifying the characteristic polynomial. I was able to solve the characteristic polynomial and found that it had these roots. It had negative 1, negative 1, negative 1. So negative 1 was a triple root. It's repeated. 2 was a single root. And then I had a complex conjugate Negative 1 plus I and negative 1 minus I. What is the general solution of the ODE, of the differential equation, for which these are the roots of its characteristic polynomial? Notice that's all you need to be able to write the general solution are the roots. You don't even need the differential equation to come up with its solution if you know the roots.
So C1 to the negative 1t plus C2t e to the negative 1t plus C3t squared e to the negative 1 or
Yep.
t.
So that's these three here.
Plus C4 e to the 2t.
Okay. And now complex conjugates always go in pairs. What's your A and what's your B?
A is negative 1.
B is.
1.
So C5.
Is e to the negative 1 or negative t cosine t. 6.
So notice how two roots still correspond with two terms in your general solution, but now they've got the cosine and sine in it. Yes?
For the C4 e to the 2t,
Yes.
why don't we have a t cubed in there?
Because it's a single root.
Okay, we only put the t's in there if they're the same root.
Yeah. For a repeated root, you start with no t, and then you have t, and then a t squared. You just
So
keep.
that's only if it repeats.
Yes. Only if it repeats. And that's your general solution.
Then you'd have to find out which one the C's are.
Yeah. Then I mean, if I gave you this is basically a 1, 2, 3, 4, 5, sixth order DE. So if it was an initial value problem, you would have y of 0 equals something, y prime at 0 equals something, all the way down to y fifth derivative at 0 equals something. And you'd have to use those 5 to find the C's.
No thanks.
I mean, theoretically, it's doable, but there are not very many real-world model equations that show up that need sixth-order ODEs to model them. I've only got 8 minutes, so I might as well talk about the spring. Let's go back to page 1.
Oh, that is
Yeah, I skipped over it. This just lets you see that this is one particular model where the result is a homogeneous differential equation with constant coefficients. So you can visualize a physical model while you're looking at these equations. So here's the picture. I want you to draw a wall and a floor. And I'm going to set a mass on the floor. And to the wall over here, I'm going to attach a spring. And if the spring is at rest, it would lay relaxed at this length right here. Okay, I'm going to do a spring shape. But what I'm actually going to do now is I'm going to stretch the spring. So this is like the equilibrium of the spring. So when you pull the spring past that point, there's going to be a force acting in the opposite direction that you're past that equilibrium. And if you're short of that equilibrium, it's going to be pushing the other direction. So imagine a little spring then attached on that end. So this here is the spring equilibrium. Now what I'm going to do is I'm going to measure y as the distance, the center of mass, is away from the wall. Okay, distance, or sorry, not from the wall, from the equilibrium point. Distance from equilibrium. Let's say this is positive and this direction is negative. So y of t is a function of time based on where my mass may start. There is a theorem, what would you call it a theorem? A law. We'll call it Hooke's law. You may have heard of this from your physics class, right? Based on the spring. Hooke's law says that the force from the spring is proportional to y, how far you are away from equilibrium, right? So it's ky, but since it's acting in the opposite direction, so for example, if y was positive, the force would be acting in the negative direction. I'm going to put a minus there. There's also, in this, the way I've set this up, because I've got this resting on the floor, there's a friction force. And we'll use the same model we used for falling bodies, that the force of friction is proportional to the velocity. The faster you're moving, the more the friction force is acting. And it's going, so it's proportional to your velocity. So it'd be like a by prime. But if you're moving in a direction, which direction is your force acting in? The opposite way that you're moving. So that's also going to be a minus. So these are the two forces acting on that mass. We know from Newton's second law that the total force acting on the system is always equal to mass times acceleration. So what we can say is mass times the acceleration is the sum of all of the forces, which would be negative by prime minus ky. And then I'm going to put plus some capital F sub ext. And I'm just going to call this any external force. So imagine I'm standing there smacking the spring every so often. I'm the external force. If external force is 0, then that's just starting the spring and letting go. Okay? But there could be all kinds of different external forces. We could have some magnets involved to create a pendulum-like operation for a clock to be able to run perpetually. So that external force becomes the magnetic force involved in an additional pull based on how far you are away. But still, if there was no external force, then you'd just have these guys. If there is an external force, we'll call it F sub ext. And all I did right here is then solve. So I should write in linear form, I guess. So this constant B in here, actually we'll go ahead and write this in. M is the mass. The B is sometimes referred to as the damping constant. The larger it is, the more effect friction will have on the system. Okay, the smaller it is, or if it's 0, there would be no friction. The K here represents the stiffness of the spring. The stiffer the spring, the greater the force for a smaller move of the spring. Okay? If it's stiffer, right, K is larger, then that spring is going to exert much more force for moving it away from the position of equilibrium. All right, so this last point to be made here is let's consider a very simple case where B is equal to 0 and there's no external force. What does the model for the spring look like under Hooke's law? It's my double prime plus 0 plus ky equals 0. Now, I'm not going to do it the way that I asked. This would be what I would do if we hadn't even talked about how to solve these things yet. But now we have a way to solve this. We can come up with what the general solution looks like. Let's say y at 0 is some, y naught. So this becomes, and we need to use a different variable since we've got m here. Let's do m x squared plus k equals 0. That's your characteristic polynomial. Actually, I like z. That's a much better choice. I'm going to use z. All right, characteristic polynomial. So then what is z equal to?
Square root of k over n. Negative k over n.
So it would be plus or minus I square root of k over m. Agreed? All right. Now, you kind of saw it up here, but I'm going to call this, just for simplification, let's let omega equal square root of k over m. That means your solution looks like a c1 cosine of omega t plus c2 sine of omega t. By the way, I would also need a y prime at 0 would be y1 to have a complete initial value problem. I don't really want to solve a specific example, but the point here is my solutions now look like sines and cosines. I get the oscillation that I expect to see. And notice there's no e term. Unlike way down here, when I looked at this problem right here, I got an e to the minus 1/2 t. And as time went on, this thing went to 0. Well, look at the differential equation. Using the constants we just talked about, what's the mass of the object modeled by this spring? 4 units, whatever, 4 slugs, 4 grams, right? What's the damping? 4. So that's your damping constant. That means friction is positive and acting on this system. And then you've also got a stiffness of 17. So with those parameters, that gives you something that has sines and cosines, so an oscillation, but it also has an e to the minus 1/2 t that forces it to eventually settle back to the equilibrium. Okay. And I'm done. You can pack up. There's, yeah, I forgot that we did the last page. First page last. All right, so 4.3 you are now able to do for Thursday, and then we'll start solving particular equations. We're going to change the right-hand side to something other than 0 now. So basically going to add external forces to our spring. I'm going to start smacking the mass around a little bit.
You said we could turn in our offline homework next time? To fix it?
Yes, since I screwed up.
You're gonna be meeting in the physics lab next time?
We should play with some toys. Now, we're going to do some projects in here, so you'll have your chance to do some of that. All right, stopping this.